From the 8 billion humans on Earth to the 1 septillion stars in our universe, there is one thing that binds us all: matter. Everything we perceive occupies a part in space, acting as the fabric of our universe. What if this perspective of the universe might be different from how we thought? What if we don't fully understand that the thing that binds us together, matter, is more complicated? And what if this mystery is a core concept of our universe and we still do not know about it? Matter as we know it is only accounting for less than 5% of the universe. This is matter that can be seen, measured, and known. The other percent is made up of dark matter and dark energy. These two things are invisible, unseen parts of our universe that allow our universe to act and exist in the way it does. Physics is quite sure it does exist, so let's discuss how it was discovered, what we do know about it, and should we fear it.
In the late 19th century, images from the budding field of astronomical photography revealed dark regions in the sky and noticed stars weren't really evenly distributed. Scientists wondered if this was because these dark regions didn't have stars or if there was some sort of matter blocking their views. Later into the 19th century, a Lord physicist by the name of Lord Kelvin wanted to calculate the mass of the Milky Way galaxy. By observing the velocity of the stars orbiting the core of the galaxy, he could use these speeds to estimate the mass. Upon doing so, he noticed a difference in the mass he calculated to the mass of the stars he can see, concluding that many of those stars, perhaps a great majority of them, may be dark bodies. In 1906, French mathematician and physicist Henri Poincaré responded to Lord Kelvin's ideas in his book, The Milky Way Galaxy and the Theory of Gases. In his book, he explicitly used the term matière obscure, which translates to dark matter. Even though he was impressed with his work, Henry disagreed with his conclusion. He responded that since his number is comparable to that which the telescope gives, then there is no dark matter, or at least not so much as there is of shiny matter. For decades, the answer remained unanswered to what is truly meant by dark matter, with some taking the term quite literally, defining dark matter as regions in the sky that lacks light. It wasn't until 1933 when the first major evidence of dark matter's existence was published and the sheer amount that exists in the universe. Swiss-American astronomer Fritz Zwicky was observing the Coma cluster and calculated that the velocity the galaxies were travelling was close to 1,000 kilometers a second. This meant the stars were travelling so fast they should have escaped the gravitational pull. He concluded that there must be much more matter in the galaxy which is keeping the stars gravitationally bound. He added that if this would be confirmed, we would get the surprising result that dark matter is present in much greater amount than luminous matter. Even though Zwicky's estimate of dark matter was off by a factor of 8, his evidence still proved two very important key factors about dark matter: its existence and how much there is in comparison to visible matter. Today, we've only scratched the surface of what we know about dark matter, but we have enough to create a basic understanding. We now know that dark matter does not interact with any electromagnetic forces, meaning it doesn't absorb, emit, or reflect light. We can only infer its presence by its gravitational effect it has on matter. We also know that dark matter only makes up about 27% of our universe, with luminous or visible matter making about 5%.
In 1998, things began to change. Physicists at the Gran Sasso National Laboratory in Italy created a detector that would soon become known as the DAMA-LIBRA experiment, standing for Dark Matter Large Sodium Iodide Bulk for Rare Processes. The DAMA-LIBRA experiment is a continuation of the DAMA Sodium Iodide experiment, which involved researching the presence of dark matter in the galactic halo, the globular cluster of stars surrounding the Milky Way, through the use of a sodium iodide scintillator. Similarly, the DAMA-LIBRA experiment uses a matrix of thallium-doped sodium iodide scintillation detectors to directly detect dark matter particles in the galactic halo. As the Earth orbits the Sun, the dark matter modulation is measured through the variation in the detector's velocity in comparison to that of the dark matter halo. The detector itself is comprised of a 5x5 matrix of thallium-doped sodium iodide crystals. Each detector is connected to two 10 cm long UV light guides that act as optical windows. These are coupled to two background photomultipliers, which work in coincidence to convert any incident photons into an electric signal. To reduce the risk of any background radiation or air interfering with the detector, the whole thing is encased in a sealed copper box, flushed with pure nitrogen, and in the center of a low radioactive multi-ton shield. Surrounding this is 1 meter thick layer of concrete for additional protection and neutron moderation. The DAMA LIBRA experiment began collecting data in 2003 and managed to collect several yearly cycles of data. The oscillations detected in the experiment are thought to be direct detections of dark matter, as a result of the Earth orbiting through the Milky Way's galactic halo of dark matter. When completing its annual revolution around the Sun is also moving around the galaxy. Therefore, the Earth should cross a larger flux of dark matter particles around the 2nd of June, and a smaller flux around the 2nd of December, due to the velocities being opposite at these points in the year. The effect induced by the dark matter particles must satisfy a series of requirements before it can be considered unequivocal evidence for the annual modulation signature. The rate must have a part modulated according to a cosine function, with a 1-year period, a peak around the 2nd of June, only found in a low energy range, must apply only when one single detector fires, since multi-interaction probability is negligible. When sensitivity is in its maximal region, the modulation amplitude must be less than 7% for typical halo distributions, but the sensitivity can be larger in certain situations. The results obtained from this experiment satisfy the expected results of a genuine dark matter signal, but the experiment is still being carried out in the present day. The SABRE experiment, sodium iodide with active background rejection, is an enhanced version of the DAMA LIBRA experiment that is beginning its data collection this year. Despite this, the DAMA LIBRA experiment has been almost impossible to replicate. Physicists across the globe have been attempting to detect dark matter, but to no avail. Initially, the COGENT experiment in the US had promising results, similar to those of the DAMA LIBRA experiment, but it was later discovered that the signal detected was a result of the background particles. Therefore, the credibility of the DAMA LIBRA experiment has been heavily debated over the years. The physicist Jonathan Davis has suggested that the signal may have been caused by neutrons scattering in the detector, which would have been derived from solar neutrinos and muons scattering around the detector. However, this theory has been disproven, given that the fluctuating rate of decay of muons does not match up with the known data for the correct time of year. Others have criticized the experiment due to its environmental fluctuations, not a result of dark matter particles. Despite the laboratory being deep underground to minimize weather and environment effects on the experiment, humidity and moisture may still be an issue that could impact the results.
Physicists may have a hard time agreeing on whether or not we have conclusive evidence towards the existence of dark matter, but it's hard to deny that they are taking a step in the right direction. Our understanding of subatomic particles is much better than it used to be, and the experiments into the search for dark matter are always being enhanced. So, one day it is incredibly likely that we will have solid proof that not everything in our universe is visible. Who knows? Maybe there is more out there than we could have ever predicted. This right direction could allow us to understand and even use this understanding to create more inventions that should shape our lives. For example, understanding radiation allowed for microwaves, medical machines, and nuclear power stations. Or it could be quantum mechanics, which allowed for flash memory drives, lasers, and quantum computing. The discovery of the way dark matter and dark energy works could result in new groundbreaking inventions.